So what I wanted to do today is to just introduce us to the Smith chart. Some of you may have already seen that. For some others, it might be something that you have seen way in the past, so it may not seem familiar, but I will start right now. Before I do that, however, are there any questions you may have from the previous problem solving session? Or you are ready to move on the Smith chart?
I do have a question about ADS. I saw some mention of it in the group chat. Is that something that we're going to be expected to use going forward with the assignments?
No.
Or is that like a supplement? Okay.
It's only if you want to use it. I think every student knows MATLAB. So you can use MATLAB, or you don't have to use any of these. I mean, ideally, the things that we will do in this class you will be able to do with these paper designs. If you want to use MATLAB for quick calculations, you can do that. If you want to use something else for quick calculations, but you are not expected to use ADS. This is not what this class is going to teach. So if you know whatever you know that may help you, you can use it. Or you can even write your own small program, you know, and use that. I mean, the calculations we're going to do will be rather simple. And we're going to do designs that are going to be what people consider in the industry 0.0 draft. It's like the beginning of the design that helps you put a system together. Obviously, in real design cycles, you really have to improve on your assumptions, improve your design. So yes, if you were to take that initial design, which is what we are going to attempt in this class, then you can optimize it and you can make it more complex if you wish, and then you will need to start using more advanced software, obviously. But not in this class. This class is to teach the fundamentals, as you can imagine. All right, so any other questions about that? Okay, let us now look at the Smith chart. The Smith chart has at least this type. There are different types of Smith charts. The one that you see here has 3 different circles that are drawn, and not all of them. They are just parts of them. So I will draw on the left to see exactly how this is generated. So we're talking about the Smith chart. Okay, on the Smith chart, first of all, we have one axis and we have a point of reference. And depending on what you measure, then the radius of this Smith chart is a relevant parameter. It does not have to be so many physical units. Now, it can vary physically, but it is whatever it is in relevant ways, and I will explain to this. So first of all, you find the center of the Smith chart, which is this, and then you define the radius of the Smith chart, which is, let's assume that for the radius, and let's see how that works here. So I will, so they said that if I do this, there, it works. That's how you create a circle on the Smith. So let's assume that this is our Smith chart, all right? I decided to take a radius and make the radius whatever I wanted. And then now I'm gonna start creating circles. Okay, let me use the red. which will have their center on the axis of the Smith chart. And also that will be tangential to the Smith chart at this point A. And I will also go through this center of the Smith chart that I call O. All right. And let me make one here. There. Oh, all right. Let me make it again. Okay, so this one, this circle goes through the center of the Smith chart and is tangential to the circle of the Smith chart at point A. And we say that this circle represents all of resistive values that normalized to a characteristic impedance are equal to 1. So every resistance value, when we normalize it to Z0, because we have to always normalize the entities, all right? So we show the normalized resistor like with an R with a bar, and all of the values of the R normalized R equals to 1. They all are on the perimetry of this circle. You see it here. All of therefore, any value here will represent an impedance that has this resistive part. So that's saying, having said that, then that takes us back to say what a Smith chart shows. Every point on the Smith chart corresponds to a normalized impedance. So any point here, for example, point P, will correspond to a normalized impedance. All normalized with respect to Z0. And we can define Z0. Here you only find the normalized values. So how are we going to find, since all of the circles that have their center on this axis of the Smith chart, like here, for example, and they are tangential to the circle of the Smith chart at this point A and go through the center, all of these circles, and this is one of them, the points on these circles, they all correspond to the same normalized resistance. So if I were to identify another point here, ZS, then this ZS would have what? A real part RS plus JXS, where the real part is 1, because it is on this circle. And then it has a reactive part, which we have not found yet. So for this P, if I want to find the real part of this P, then so let me go now to this to the Smith chart. Let's assume that I have a point here. P, my P point is here. P. Okay, let's assume it's the same point with the other I had there. Now, I want to find the circle that goes through point P and is the circle of the constant normalized real part of the impedance. So I will draw a circle here that goes through P, and I can see it, but I will have to draw it. Goes through this Okay, that did not work very well. Cut. I'll do it. I did it too ragged. I think it was too ragged what I did. So let me do it. Try again. No, that did not work either. Okay. Okay, that worked. So this is the circle, a little bit bigger. In fact, I was very close to being good. Okay. Now, how am I going to read the normalized value? The Smith chart, oops. Yeah. The Smith chart here, if you bring it much closer, you see that this circle goes through I think I made a mistake when I did that. Bring it here. There. And here. Okay, very close enough, I would say. Okay, well, close enough. I'm not gonna try to fix it. So if we are growing this, we find that it goes close to 0.3. All right, all of these are approximate. Now, I mean, if you do it more carefully, and if you move it through this point, it's going to 0.3. So here. So as a matter of fact, this number here shows the value of the real part of this point, okay, of this impedance. So Z sub P here, normalized, has 0.3 as real part and has an imaginary part, which is also normalized. We'll find it next. Do you see that? Any questions about this? Okay. Now, when you look at the Smith chart, we also have another set of circles, and those other circles, they are not shown, all of them. So for example, you will see circles here, I'll use a green one, that go like this. All right. These circles, if you were to draw them correctly, you will see that they are circles whose center is along this line here, somewhere up. And these circles are tangential to the axis of the Smith chart at A. And we only need, for passive components, we only need this side of this part of the circle, not all of it. Now, how am I going to find, and these ones, all of the points of all of the green points are giving you the same imaginary part, have the same imaginary part. So X S of Z naught, which is the normalized XS, so normalize here. This one, the value is gonna be specified by where exactly, at what point this green circle intersects with the outside perimeter of the Smith chart. So we will go, if this is our P point, all right, and if we want to draw this for point P, then, and if I check which circle goes through that, it's this one. Okay, and then when I go here and read, that gets me to 0.5. So for this point, z sub p, for this point z sub p, and I should put p here. X sub p, and from the green circle, the green dotted line, X sub p normalized is 0.5. Everything that is on the north side, on the upper side of the Smith chart, all of the values here for the reactances are positive, and all of the values underneath it are negative. Therefore, since this point is up here, is positive, and the total impedance, Z sub P, will be 0.3 plus J 0.5, and that's normalized, which means in order to find Z sub P, I will have to multiply the normalized values with the characteristic impedance. And then that characteristic impedance is whatever I use for my designs, which is normally a 50 ohm. We normally use a 50 ohm. All right, so this is how we find points. So, or from a given point, we find the values. If I want it, if somebody gives me that your impedance now, somebody gives me that I have a Z load normalized, which is 1.3 minus J 0.9. Okay, and let's see where the point is. First of all, I have to find this one. I have to find 1.3, which is the resistive part, and normalize is 1.3. So I have to look where are the values of 1.3, and it's here on the Smith chart, which means that all of the circle points of the circle that go through this 1.3 point, and this is a constant resistance circle, all of these points have the same resistance normalized, and it's 1.3. All right, I'm not gonna draw all of it. I will stop here somewhere. Okay, now, what is 0.9? 0.9 is with a minus, okay, this, and 0.9 gives us the reactive part of this load, Isabel, and we have to see where is the circle that has the equal, all of the points have the same reactive, normalized reactive part, and then it's negative. So I have to be in the lower, on the lower side of the circle, go and look for 0.9, which is here, and then put here a note and say, oh, this is the point where the circle of constant reactances goes through and is negative. So all of the points of this circle here have the same normalized reactive part in the impedance, which is minus 0.9. So this is my Isabel. So here I have Isabel normalized. Okay. Do you have any questions so far about this? Yes? No? Is it all known? Do you remember those things?
I'm starting to remember a little bit now.
Okay. Anybody who has not seen this before? Okay. Now let's go to another one, and I have to, let's see, we need one more Smith chart here. So, document, I will make a copy. Let's see how I got this one. 1 second, let me, what I can do is to erase those things since they're gonna be, I'm not gonna have those available, so you can just take, you guys take screenshots because I don't have as many Smith charts. I will erase that and then I will rewrite, go to the next step, okay? So you can go and take screenshots. And if you're kind enough, you can send them to me as well. Is that okay? Who will take the responsibility to take a screenshot out of those? Who can find it easy to do that? Any takers?
I can take it, ma'am.
Thank you very much. Thank you. Okay, so now I can erase this. I have to tell you, I'm not that familiar, and I had to go through a lot of trouble to get this Smith chart on. I'm not very that much familiar yet with this software. Okay. All right. Now we can go down here, or maybe I can do the same here. What are we going to do next is the following. I'm going to draw for the next one. I'm going to draw a transmission line. So here, we have a transmission line. And this transmission line has a characteristic impedance Z0 and has a load at the end, ZL. All right. And now I would like to find, it's a distance D. Okay. Then, first of all, let's assume that somebody gives you the following, that ZL, not normalized yet. We have not normalized it, is 100 ohms and plus J 50, okay? And that in ohms. If it's like this, so most probably ZL is nothing else but a resistor in series with an inductor. Do you agree? If I were to think in terms of a circuit. And if that has an inductor, then R is going to be 100 ohms and omega L is going to be 50. Do you agree? Yes?
Yes, ma'am.
All right, thank you. Thank you. I'm asking because I don't see anybody. And I'm just lecturing to my notes, all right? So that's why I need to hear that there is some response. Okay, now we take this, make it smaller, move it there. Let's assume also that D, what happened? D, could you, what the heck? Here, D is 0.3 of the wavelength. All right, so that gives, somebody gives it to me. And they say, number one, find the input impedance here. How am I gonna do that? Question number one. So I'm going to this Smith chart. First of all, I have to find Zisa Bell, normalized. So I have to normalize Zisa Bell, and Zisa Bell here, normalized, is 100. I gave you Z naught is 50. And it's 100 divided by 50 plus J 50 divided by 50. So it's 2 plus J. I want to find this point on the Smith chart. So I'm going here, 2. I have to find the resistive part, which is 2. So all of the circles, I will indicate that with red, and then I will indicate the other one with green. So all of the circles that have, all of the points that have the same normalized real part, which is 2, will be here on this circle. Okay? And I need now to find that particular point. Therefore, I have to find the other circle where all the parts have, all the points have the same normalized and reactance, and it's 1, positive. So I'm going to find here where is 1, and 1 is here. So I'm drawing this circle where all of the points have the same normalized reactance. And therefore my Zisa Bell is right here. That's my Zisa Bell. Okay. Now we are gonna introduce a new type of a circle, and this is going to go through point ZL, and it's going to have its center at the center of the Smith chart. The center of the Smith chart is here. All right, so here. So now I'm gonna draw this, and I'm gonna use this color, and there. Perfect. All right. What is this circle? This circle is called the constant VSWR circle. So this is called the constant VSWR circle. This is equal to a constant. Why is that? Let's work a little bit on transmission lines to see why that, why this is the constant VSWR circle. When we have a transmission line, and here we have a Zisa Bell. When at this point, how much is the reflection coefficient? Gamma sub L equals ZL minus Z naught over ZL plus Z naught. But when I normalize ZL with respect to Z naught, it gives me ZL minus 1 over ZL plus 1. Okay? And then in our case, if you can replace that, you're going to find a, let's do that as a matter of fact, 2 plus J minus 1 over 2 plus j plus 1. And this gives us 1 plus j divided by 3 plus j. And now we would like to make that in a form that is like a magnitude plus a phase. All right, do you remember how to get a complex number that looks in the form of a ratio of two other complex numbers and then get the magnitude and the phase? Do you remember how we do that? How do we manage that?
With phasors?
Yes, you can get the phasor for each side, numerator and denominator. All right, so let's do that. I will not do it like this, but let's try that since you suggested it. So 1 plus j, how much is that? That is the, you can do it with like, it's square root of 2, all right? And then it's e to the minus j phi, where phi, or plus j, well, let's put plus j for a moment, where phi equals the inverse tangent of 1. And how much is the inverse tangent of 1?
Power of 4.
How much is it? It's an angle.
45 degrees.
45, yeah, of course, thank you. I should remember that. 45. So this one gives us square root of 2 e to the j 45. And then we have 3 plus j, which is going to be square root of 4 e to the j phi prime, where phi prime is the inverse tangent of 1 over 3. And how much is that?
18.4 degrees.
Thank you, 18.4 degrees. So this one here is 2 e to the j 18.4. So practically now, let me squeeze those a little bit. So we have that gamma sub L going back equals square root of 2 up here, e to the j 45, divided by 2 e to the j 18.4. And that is 1 over square root of 2. And then we have e to the j 45 minus is close to 25, 23.6. How much is it? 22.6.
26.6.
Minus 45.
Yeah, 26.6.
18. Yes, 26. Thank you. You are right. 26.6. 26.6. Perfect. So let's go further down on this one. Therefore, the magnitude of gamma L is how much? 1 over square root of 2. Do you agree? Which means on and then how much is gamma at every other point? If I am now at this point, distance. Oh. If I am now at this distance L,
Professor, we can't see the screen anymore.
okay. What happened? My husband is calling me, if you can believe that. All right. Jesus Christ. Hey, what's up, Spiro? I have a lecture. Okay. Okay, so you should be able to see this now. All right, so with the, this is 1 over square root of 2. Then at any other point at a distance L, gamma then becomes gamma sub L, the magnitude of gamma, e to the j phi. However, we have found a relationship that says this is gamma L e to the j2 beta L. Do you remember that?
Yes.
Good. Okay, and with
Professor,
that, yes.
shouldn't the magnitude of the 3 plus j be square root of 10? Because square plus 1 squared and square root.
JB,
3 plus j should be like square root of 10, the magnitude.
3, yes, I got 3. Oh, thank you. Perfect. Yes. 10. And then I have to correct this one, which is square root of 2 divided by square root of 10, and that's square root of 5. 1 rather. Okay. All right, thank you. Sometimes when I do that, I don't pay, I have so many other things here and I don't pay attention. So thank you for correcting it. Now, that implies from this one here that the magnitude of gamma at any point on this line is equal to the magnitude of gamma L. All right, so the magnitude of gamma is the same everywhere on this transmission line. And from that, we conclude, I have to make it smaller. Well, does not want that. So from that, we conclude that gamma magnitude in this particular case is going to be equal to 1 over square root of 5. Now, do you remember what is the VSWR? Have you seen this before?
Yeah.
Okay. What is it? Can somebody tell me?
1 minus gamma over 1 plus gamma.
Yes, that is the relationship. Very good. Is 1 plus gamma magnitude, 1 minus gamma magnitude. And what does it represent?
The standing wave ratio on the line.
Yes, what is the standing wave ratio on the line? Is the V max over V min. Do you remember that? The total, V max over V min, is a ratio of the maximum voltage, total voltage on the line, divided by the minimum total voltage of the line. All right? So if I have, therefore, a transmission line that ends at a resistive load or at a load, any load that has a resistive part too, then somehow the voltage is going to look like this. Depending, of course, if this is from 0, it's going to look like this. All right, depending, of course, on whether it's going to start here or somewhere else, depends on what the phase of your reflection coefficient at the end of the line is. Now, this is max, V max, this is total V magnitude. Because obviously we don't have a phase here, but V max magnitude here is this, and V max minimum is this one. And VSWR shows the ratio of the two. When the load at the end is only reactive, there is no resistive part. So here there is a Z, which is R plus JX. But when your ZL is only reactive, then depending on what it is, this is gonna look like this. All right, so what happens in this case? V maximum will be somewhere here, and V minimum will be at 0. All right, and in that case, the VSWR has an infinite value and shows a very high reflection from the load. All right, very high reflection. When ZL, 1 second. When ZL equals to Z naught, then your total line, your total voltage is just a line. It goes like this. The maximum and minimum are identical. And it's only the amplitude of the incoming voltage. Why is that? Because there is no reflection. So in this case, your VSWR equals to what? 1. So practically, the VSWR is a very important parameter. The VSWR is a very important parameter, and when it is 1, it shows that we have a complete match. When VSWR is infinite, it shows that we have only a reactive load. At anything in between, it shows every other case where you have a resistive plus a reactive or minus a reactive load, okay? So the VSWR here is extremely important. If the value of the VSWR is 1, then practically you are at the center of the circle, and then you see here is where you read your VSWR. You read it along this line here. On the chart, and it starts at 1. See, 1. If I know that I have a match on my line, this one, if I extend it, if I write the line, which is perpendicular to this axis, to the axis of the Smith chart, it goes here. So the center of the Smith chart corresponds to VSWR, which is equal to 1. So the center, if I go to the center of the Smith chart, that means that I made my gamma equal to 0. So the center, when we try to do matching problems, we always have to go to the center of the Smith chart. So when we do matching, we match or when we design a matching network, we always go to the center of the chart. This is our effort. So that's what you always have to do. But you cannot just move any direction you like on the Smith chart. You can only move along those three circles, either the VSWR, and whenever you move on the VSWR circle, it implies that you are moving along the line. And whenever you are moving on the resistive circle, that means that you are changing your resistance. Whenever you move on your reactive circle, that means that you have changed your reactance. So you move along the VSWR circle, you move along the line. When you move along the resistive circle, or it means that you, when you move along the resistive circle, it means that you have kept your resistance the same, but you're changing your reactance. When you move along the constant reactance circle, you keep your reactance the same and you are changing your resistance. And the only way to change resistance on a transmission line is by adding a resistance, all right? Because practically, when you move along the constant VSWR circle, you change both. You change both resistance and reactance. When you move along the resistance circle, you keep your resistance constant, you only change your reactance. When you move along the constant reactance circle, you keep your reactance, you only change your resistance. So these are the three directions we can take when we move on this VSWR circle. Is that clear? Any questions along those in relation to this? I don't hear any. Okay, so I'm gonna do this here. And now we are gonna solve a problem. I guess this is the idea. The more problems you solve, the easier it's gonna get for you to use this. All right. Do you have a particular matching problem you would like me to solve? Do you want me to, yeah, go ahead.
I remember you mentioned before that homework 2 could have been solved with the Smith chart, so that might be a good.
Yes. Could you remind me? You have to, I will the exact thing, so I don't have to bring it up because then I will lose the screen. So just
Pull it up myself.
problem 3 of homework.
Problem 2A, I guess, of homework 1. Yeah.
Okay, homework 1, problem 2A.
Yeah.
Yeah, homework. Sure. Okay. Remind me how that was. It was I need to remember, the reflection was coming from the transistor, wasn't it?
Yeah, and that was gamma S equals 0.5 with 145 degree phase.
And was something like that. Am I right?
Yeah, and then there was that resistive load on the end.
Yeah. And here was a Z sub S. How much was this Z sub S?
So there actually wasn't a Z sub S there. There was a resistive load. The load was on the left-hand side, and the resistor was on the right-hand side. And the left-hand side resistor was 50 ohms. And on the right-hand side with the transistor, there was a gamma S,
Okay.
a gamma S equal to 0.5 with the 145-degree angle.
0.5, 145.
Yeah.
Okay. So that's gamma sub S. And then that was, and we wanted to find the lengths.
Yeah. So the top part is Z01 and L1, and then like the stub part is Z02 and L2.
And if I remember, Z01 was 50.
And Z02 is 80. Yeah.
Okay. So here we have a gamma S, all right? So to see how you can solve this problem here. And then your load on the left side is R sub L. So let's assume that I normalize as I do most of the time, and unless I ask you something else, you should keep that in mind, that we normalize with respect to 50 ohms. Therefore, this is gonna be my R sub L.
It's 4 o'clock.
R sub L that I will normalize, obviously, not here. So my R sub L normalized will be 1. The Z01 normalized will be 1. Z02 normalized will be 1.6. And then I have my gamma sub S. Now, what we want to do here is see a gamma sub S when I look to the left. So the equivalent that I can write this is the following. I could write this as a load here to the at the end, Z sub L, or Z sub S, excuse me, that creates a gamma sub S, Z sub S, that creates a gamma sub S reflection compared to Z naught. And then I can have a transmission line here. Let me do it a little more nicer, because this is a little too weird. Okay, so here I have a load Z sub S. That's my transistor. Then here, I put a transmission line. That has Z01. Then here at this point, the transmission line is connected to 50 ohm. All right. Now at here, I put a short circuited stub. And looks like this. Let me do it a little better. Okay. And this has length, this one L1, and this one L2. Okay, Z02. All right. So the equivalent to this is knowing Z sub S to be able to find at this point, let me call this one A prime, B prime, okay, here. And let's call this CC prime. Okay, so the equivalent to this, I can look at this as following. first of all, I need to remember that a short-ended or a shorted stub gives what here in the input? Gives only a reactive part, okay? And of course, whether this is gonna be positive, negative, or what it's gonna be depends on this value. Do you agree with me? Why is that? Because you remember we said that a Z input in a stub from theory, we said that ZS input is nothing else but Z naught. I will rewrite it. So it's JZ naught tangent, but I will rewrite it to show you how we get it. All right, where ZL is 0. So what is this gonna give us? Equals Z naught J tangent beta L2. Do you agree? So this is gonna always be a reactance. All right? And also, we can write it in the reactance form. And that can have the same form with all reactances. Make sure that when you write reactance and you use the same formula, they are all reactances. Also, I wanted to say that you can also use the Smith chart, not only for impedances, but all for reactances, as long as everything is in a reactance form. And you're careful when you go through series or shunt configurations, okay? But if it's all a reactance chart, then you do have the same circles, but they're all reactances, the values. That's what you need to keep in mind. You don't get a reactance on one end, but you read impedance. So either you go only for impedances or all for reactances. Now, in this case, because we have a shunt configuration. So let me write here, since now we know that the stub gives a reactance, then I can redo the graphic. And here is my load in reactance form, admittance form. And then here is my stub also in admittance form. And this is L1. And then here is my load, but in the form of a conductance, 1/R. Okay, you cannot just keep some impedances or resistances and some admittances, all right, or conductances. You have to convert everything. So because of the shunt configuration, I converted everything. And if you convert everything, then you can use the Smith chart. Now, to be able to achieve the same goal as before, and then show that here I have this gamma S, because here practically this is the inverse of ZS, all right? Yes. Okay, and you remember that this is the same ZS without there, and this is stub, okay. So this is ZL as load. Okay, so this is equivalent to saying that I have here, because this is 1/50, that I see here a 0 reflection at this point, which I have named AA prime. All right, so is this at A prime gives me 0. All right. If I write the reflection coefficient in general, let me look at this. I wrote it above at some point. I have not written it yet. But in general, we have written reflection coefficients in terms of impedances or normalized impedances. How am I going to write it in form? Since everything is an admittance form, I have to transfer these to admittances. How am I going to write that? I'm going to write it as 1 minus ys yes, and 1 plus ys. Do you agree? I divide both numerator and denominator by z sub s, and then I have that formula. All right. So the only thing I have to do is from gamma s to find ys. And as a matter of fact, what this is, ys is going to be, let me see, 1 plus, I think gamma s is, yes, 1 gamma s. Let me just do it without, don't remember the whole thing, make sure that I don't make a mistake. So it's gamma s, 1 plus ys equals 1 minus ys, which means that ys 1 plus gamma s equals 1 minus gamma s, which means that ys is going to be 1 minus gamma s divided by 1 plus gamma s. All right? And then from there, ys normalized to 50 ohms, to 1/50 ohms. It's a 50 ohm impedance system, all right? So y naught is 1/50 ohms. So this is where y naught is 1/50. And this ys normalized is going to be 1 minus 0.5 square root of 145 divided by 1 plus 0.5 square root of 145. Can somebody find that and let me know how much this is? If you have a calculator that can do that. Okay, did you guys find it? How much is point?
I don't have a calculator on hand, but I can go grab one if anyone, if everyone else is.
That's all right, don't worry. Let me see. It's 145. Cosine, no, 145 cosine minus. Let's assume that you will find, well, we need to find it, otherwise we are not going to solve this problem. So 1 and then is minus 0.8, say approximately 2. And then I have 145 sine plus j, what the heck? All right, plus j 0.57. And 1 plus that. Which gives 0.5 times 0.82 equals 0.41 minus 1 equals 0.50. It gives 0.59 minus j 0.57 times 0.5 equals 0.2, 0.2 say 9, and then here it gives 0.5 times 0.82 equals plus 1.41 plus j 0.29, and this one gives square root 0.59 equals 0.35 plus 0.29 times 0.29 equals 0.08. 1.41 times 1.41 equals 1, let's say 2 plus j 0.08, and then e to the j phi 1, e to the j phi 2 here, which is 0.35 plus 0.08 divided equals, okay, 0.35 plus 0.08 equals divided by 2.08 equals, and that's square root. And that is about 0.45. Okay, and then we have 0.29 divided by 0.59 equals, and then that's like that. Okay. Let me find this one. Did anybody else can anybody else do it faster than I am? So 0.0, buddy, find 0.49, and the other is 0.8 divided by 2 equals 0.04. And okay, 0.49. Calculate. This is 26. And 0.4, calculate, that's 2, or 28. 26 minus 2 is 8 minus 24, 8 to the j 24. Okay. And a minus, there I forgot, so it's minus 24 plus, rather, no, minus 26, 28. I think that's correct, but it does not matter. We need to get just this number, is important. So ys normalized is this one, okay, which in fact has the 20 8 negative, and that is sine. So phi 1, that's not possible. Cosine 28 negative cosine. It's 0.88 times 0.45 equals, and that's 0.34, and then minus 20 plus 28 negative sine times 0.45 equals, that's minus j 0.21. Okay, so these are the normalized. So we said we are gonna now have to do the following. We have to go from a load ys to find the center of the Smith chart. You remember what I said? Every time you match totally, so you have to get to the center of the Smith chart. So let us try first of all to find where is the normalized admittance of 0.34 minus 0.21. So 0.34, now we are using for admittances. You need to remember that, admittances only. 0.34 is somewhere here. All right, so all of the points along this circle have the same conductance values, normalized. And goes like this. And now minus 0.21 is here, minus 0.21 is somewhere somewhere here. And all of the points on this circle have the same admittance, reactive part of the admittance. So the point, our load y sub s normalized, which is the load in this particular case, it's right there. Okay, now from there, which is the load here, from that point here, we have to go to the center of the Smith chart. All right, but first of all, we have to move along a transmission line. All right, you see the transmission line, L1. We have to move along this line from the load, which is our ys, to find the stub. So we are moving towards the load. So here you need to remember, it says wavelengths towards generator. Our generator in this case are to the left of us. So if I wanna move towards the generator from ys along this circle, where all of the red one, on the red circle, all of the admittance points are the same. And I will have to move, not only on this, on the constant VSWR circle, excuse me. So we have to move from ys along this line. Therefore, we said to move along this line, we have to move on the constant VSWR circle, so blue. And I will write it here, the constant, let me see, I will try. No, did not get that. We'll try again. There. Okay, not bad. Here. So I can move, this is the constant VSWR circle. I can move along this circle and I can move to the right. So I will go like this. And I will go until when? I will go until this point here, where this point has all of the real part to be normalized equal to 1. And that is gonna get me exactly here. Let me do this with kind of a, here, it's gonna get me to this point. So this point here, y in at a prime is this one. And why is it important to stop only where I find the real part of y in a prime normalized is equal to 1? Because if I add the stub, the only thing that the stub will do is to change the reactants, nothing else. So the reactive part, I mean. Usually we call to be accurate with the use of the words is called susceptance. But in any case, we call it to be able to cancel the reactive part of the normalized admittance. We add the stub, or reversely, the stub can only impact the reactive part of an admittance. So we have to go along the line by a distance L1, which is gonna get us, and that's the yellow that I have shown you there, which is gonna get us from our load, which is here on the beginning, ys, to the point y in at AA prime. And then from there, now I am on the constant conductance, normalized conductance circle of 1. And therefore, if I move now, use a different color, I'll use this one. If I move now from here like that, on the circle, maybe I need to use red because that's what we used. If I move along this circle, which has, for an admittance chart, a constant real part in the normalized admittance, then I get to the center of the chart. So from point B, let's call this is point B. We called it point B, all right? So if this is point B, this is my point B. I go from B to A. Here I add to the A, I add the stub. And then I go to the center where I have a total matching condition. All right, so practically my input impedance at the center is gonna be, or admittance, normalized is gonna be 1, which makes the normalized input impedance to be 1, which makes the input impedance to be Z0. So practically it's gonna be 50 ohms. Any questions so far about this part of the exercise?
Just making sure you treated the transistor source as a load because you knew from gamma S that there was a reactive component. And that's why you went that direction as opposed to the other way.
No, it's easier to always have as your destination the center of the chart. All right. So when you design, you always design to make your reflection coefficient 0. In that case, you had to provide something which is different. I mean, if you were to look the other direction, then you would have to make your reflection coefficient there not 0 but gamma s. So it was easier for me to, and then it will get a little more complicated, not different, but a little more complicated on the Smith chart. So I decided, for your sake, to turn the problem. So I consider the transistor as my load. Since they gave me the reflection, practically I know its input impedance, Z sub S, and that is my load. And then now, since I know that at the end I'm going to have a 50 ohm load, which is like, could be my source, all right, ideally, then I know that I have to match to 50 ohms, which is the resistor at the end on the left. And that's why I did it.
Okay, and that's where you got the gamma AA prime equals 0, and that's like it was your target.
Uh-huh.
Okay, great.
Now, how do we, from this, measure the lengths? All right, because yeah, we did that. We got to the center of the chart, but in reality, the solutions are the two lengths. So here's how we do this. We draw, if you want to really find the length, you have to connect and say from point B to point A, I'm traveling along one line, all right? So if I want to find how long I had to travel to get from point B to point A, you do the following. You connect, and I'm using this color, you connect the center of the Smith chart with point B, and you extend it, all right? And you look at where, you remember that we are traveling towards the generator always. So look at the wavelengths along the generator, and everything that you read is on the outer circle. It's like on this one. Everything you read is on this circle, all right? Towards the generator. If we were to go towards the load, it's the lower circle. So I have to look all around this circle and come and read the value here. And the value here is this one. And if I am to write it, it's going to be 0.46. That's a value. We are gonna, and this is usually in wavelengths. All right, everything that you read here is in wavelengths. Then I'm going and connect the center with point A. That's the other end of the line. So here, the same, I will do this. Okay, and then I'm going here and read this number on the outer circle. And this is 0.17. Okay, now what happens here is there is a discontinuity in the value. So the circle is usually has to be continuous, but from 0.46, it goes to 0.5 and then it stops. So you find the distance from 0.46 to 0.5, which is 0.04, okay? And then you add this, and then it starts from 0 to 0.17. So practically you have to find the following. You find here, how much is the difference, the distance from here to the center? So it's 0.5 lambda minus 0.46. So this distance here is 0.04 lambda. And from the beginning, from the origin 0 to that point here, it's 0.17. And therefore, to find L1, I add the 0.04 lambda to 0.17 lambda, and that gives me 0.12 lambda. It might be not quite accurate depending on what I did with my calculations here, but I just wanted to show you the process. Okay, and then how am I going to find now the length of the stub? For the length of the stub, then it's easier because I have to move from this point A to the center of the stub. And also go there from, there I go from the source to the load, all right, as I find it. I go from the source when I move, because the point A is where, in fact, I can say that I'm moving from the center O, which is the matched condition, to this point A. Okay, I have to see how much is the reactance that I have that this stub adds. So to find the reactance of this red line, which I'm going to show like this, so look at this one. This corresponds to pure reactance. This is exactly what the stub adds. To find that, what do? This one at the right at this point, the reactance is 0. All right, 0. So practically to find the reactance that is added at point Y in AA prime to make it to 0, it's like this one is practically the opposite of this, all right? Because Y in AA prime has a reactance of 1.2. So let me write it here to see what I'm saying. At Y in AA prime, before we add the stub, this is equal to 1 plus J, whatever the reactance is of this, which is 1.2. So plus J 1.2. And then at that point, we have the stub, the admittance of the stub, parallel to, this is Y in AA prime, and this is the admittance of the stub normalized, okay, in. And the total of these, is normalized equal to 1, all right, is 1, which means that this is equal to 1. Therefore, the total, this one total here, let me write it, is Y in at AA prime plus YS in, which means from there that YS, the input impedance or the equivalent admittance that is created, reactive admittance that is created by the stub, is equal to 1 minus Y in AA prime, which is 1 minus 1 plus J 1.2, which is minus J 1.2. So we found 1.2 from here, but in reality, the stub has created this negative 1.2. So to really find the length of the stub, we start at negative 1.2, which is here. And then from there, we go, or in fact, we look at where is 0, but then we have to move. Okay, so when we go from to find the negative 0.12, which is the input of this to the stub at this point, when I have to find the length of the stub, that means that I move away from the input of the stub towards its short circuit. When the stub is short circuited, what is the load at the end? In terms of an impedance is 0. In terms of an admittance, what is it? Infinite. Which means the infinite of an admittance is here. So I have to move from this point here, like this, because I'm moving away from, I'm moving from the generator towards the load. I'm going towards the short circuit. So the length of the stub, it has to be from here, okay, and then here. All right, so I will have, that's okay, it's not very accurate, this one. Ah, good, move this one. Approximately. So here, it's 1.2, but here is the value. The value here, you're looking again at the inside, all right, now because I move towards the load. So I'm looking here at the value. So I'm going from 0.25, 0.23, and then I continue on this lower circle and I come here. And it's 0.46 something. It's a point, in fact, 0.04. Okay, so the distance between 0.25 and 0.04 is just the, well, you have to 0.25 minus 0.04 is 0.25 minus, so it's 0.25. 0.25, the distance, minus 0.04, which makes it 0.21. 0.21 lambda, and that's L2. So that's how you find the dimensions.
Dr. Katehi? Wouldn't the negative 1.2 be at a different spot than where you drew that line? I'm not sure, but I can't really read the chart.
I mean, yeah, I moved it maybe here, huh?
Well, wouldn't it be like down towards the middle, like kind of like the opposite of the top part? It's like the mirror over the x-axis, I guess you could say. Like, isn't the 1.2 down by the bottom?
Yeah, wait a second. I measured this one to be minus point. Well, let me see what I did. Let me remember. It's more. I measured the distance to be minus 1.2. Okay. And minus 1.2. This is 0.02, isn't it? this is 0.12 instead of, maybe that's what I've done.
Yeah, so yeah, it'd be like down there, yeah.
Okay, sorry. I looked at point, yes. So, okay, we'll do the same, but the value is gonna be different. I just placed it where it's 0.12 instead of 1.2. There, thank you. Thank you for paying attention. Okay, here. And that then in this case is 0.12, so the distance. And here we measure what, 0.14, close to here. All right, so this is 0.14. Am I right? So 4.31, 11. Yeah, what did I say? 451, 11. Am I right? So it should be 0.11 lambda. Any questions? Would you like to see anything else? Now it's already 4:45, so maybe next time. Would you like to see more on Smith charts?
I do have a question about the last problem solving session. There was a portion of problem 2 that asked for something with the voltage, if I remember correctly, and we didn't get to solving that. Is there a way that maybe that could be like the solution that could be appended to the solution you posted so we could check? Or
Remind me, let me write it down again. You said it was problem 2.
yeah, it was problem 2 from the problem solving session. I think I have it pulled up 1 second. So,
And I will make you, could you share it? Could you, do you have it in front of you?
yeah, sure, I could do that.
Yeah, could you share it?
Do you see it here? So this portion right here, this find VBB prime, total voltage applied at ZAL. We didn't get to solving that. We just
I don't believe I see anything. I have to let mine go. Stop. Okay, sorry. Now you're ready. This one.
So this part right here is VBB prime. We didn't get to solving that.
Okay. So I will try to solve this next time.
Sure, yeah.
Could you send me a note? There are so many things right now running in my head. So if you can send me a note so I don't forget it.
Sure, yeah, I can send you an email.
That would be great. And please send me your your screenshots so I can give them to students. And then only if you have the ones that they are with the corrected numbers. Because I'm solving these problems out of my head, and a lot of times when I do some mistakes with the numbers, and thank you for paying attention to it, because sometimes I miss, I get in my head different numbers. So thank you for helping me with this, and send me please the screenshots that have the correct numbers there. If you could do that, I would
Already
appreciate.
sent them, ma'am.
Oh, thank you. Thank you so much. Thank you. I appreciate it. Very good. So I will see you next time, tomorrow, obviously, and then next time for the problem solving session. Thank you.
Thank you.
Thank you.
Thank you.